Alrighty, today we're going to be looking at the derivative of the inverse function. Okay, so few examples. So just to remind you, a while ago, maybe in algebra, you looked at finding an inverse to a linear function like this. If you wanted to find the inverse, you would just swap x and y and solve for the new y. In this case, you would get you get like 1/2 x minus 3/2. And so if you graphed these, you would notice something pretty interesting, and that is that they are symmetric about the line y equals x. So let's look at the first one. The first one starts up 3 with a slope of 2. So it looks something like that. And the second one starts down 1.5 and has a slope of 1/2. It'll end up hitting this point over here, 3, 0, whereas the first one hit the point 0, 3. And so basically all of the x and y values are flipped for the two functions. Now, there's tons of inverse functions out there. And you can get all of them by just swapping the x and y values and solving for the other. So like for example, if you're given the function y equals x squared, you could swap the values and solve for y. In this case, we're only going to take the positive x. So that's because for inverse functions, you want them to be what's called 1-to-1. So don't draw this yet. Basically, if you had drawn a complete y equals x squared function and then rotated it about reflected it about the line y equals y equals x, you would get this thing, which is actually not a function. So part of the reason that happens is because the function is not what we call 1-to-1. In other words, there's not for every x value, I should say it like this. You can get, for this function, you can get multiple x values that have the same y output. So for example, for this one, 2 gives you 4, and so does -2. And that's why when you reflect it, well then the x value 4 has 2 y values associated with it, with the inverse. So you need 1-to-1 functions. So for this one, you can only take the positive x. So you would take this part of y equals x squared, and square root of x would be like this. You wouldn't take the negative square root x. And notice how those are symmetric about the line y equals x. Lots of others. I'm just going to go through a couple others real quick. If you remember doing tangent x, so tangent looks something like this back in pre-calculus. And, inverse tangent looks something like this. You remember learning about y equals e to the x. And maybe you remember learning that there is an inverse which is y equals ln x. So I'm just trying to point out that there's a lot of really interesting functions that have interesting inverses, and we're going to want to be able to find out their derivatives too. In particular, the inverse trig functions and the natural log function. So let's start with just the basics. Theorem. Derivative of the inverse. Okay, so the if statement's a bit of a mouthful, so we will assume that f of x is differentiable and 1 to 1. So that means it has some inverse, we'll say g, which is equal to f inverse of x. That -1 there means inverse, not like a negative exponent. Okay, so then we say if b is in the domain of f inverse and the derivative of f inverse of b is not equal to 0, then you'll see why that's important in just a second. F inverse prime of b is equal to 1 over f prime of f inverse of b. So this is why we actually introduced the g of x, is just a way to take away so many superscripts. So you could also write this as just g prime of b equals 1 over f prime of g of b. Looks a little less chaotic, but g is just the inverse of f. So this is our theorem. The proof is actually pretty straightforward. So you learned a long time ago that if you plug in the inverse function into the original function, you just get x. And so if you kind of work your way out, so x is at the center here, so x goes into your inverse, and then what comes out of that goes through the original function, and it comes out the same as it was before, just x. So you can imagine doing that with, say, sine of inverse sine of x, or e raised to the natural log of x, or something like that, and you'll see that it's true. Or just the square root of x squared. It all gives you x. Okay, so since that's true, what you do is you take the derivative of both sides. And since we've shown that the chain rule is true, we know that the left side is just the derivative of the outside, leaves the inside the same, times the derivative of the inside. Okay, all of that's equal to derivative of x, which is 1. So then you just solve for f inverse prime of x. So that's just as simple as dividing both sides by this term right here. So you find that f inverse prime of x is 1 over f prime f inverse of x. QED. There's a geometric way to understand this. So I'll write here geometric approach. So this one works by, say, taking, so you've got your line of symmetry, y equals x, and take some function. So we'll just do one that looks like natural log and one that looks like e to the x to keep it pretty simple to draw. Now, if you picked a point on 1, let's say A, B, then the point reflected over that corresponds with that would just be B, comma, A. And you can actually see that if you draw tangent lines to those points, that well, let me actually make that one a bit more pronounced. Oops. Okay, let's open this one. Trying to be dramatic with the angles here. You can see that actually the slopes are reciprocals. Slopes of those lines are reciprocals. So then here, for the blue one, the slope of that line is, well, it's a tangent line at B. And since we're calling this first curve on the right, that's your f of x. And the second curve is your f inverse. Well, then the slope of the blue line is just f inverse prime of B. And the slope of the green one is f prime of A. Okay, so the reciprocal thing, I know that f inverse prime of B equals 1 over f prime of A. Well, so think about our inverse stuff again. F of A is B, so f inverse of B is A. That means you can rewrite all of this as f inverse prime some point B is 1 over f prime. Instead of A, put f inverse of B. Done. So that's the geometric approach to seeing derivative of the inverse. Now there's a few ways that this comes out in solving problems. One is just using the formula itself to figure everything out. It's like, for example, if you were asked, find g prime of x if g is the inverse of some function f, and that function is defined by x to the fourth plus 10. Well, now think about it. You want to find g prime at some for x. That means, based on a thing that we proved, you're going to need to find, well, what is g of x, or f inverse of x, and then what is f prime, and then what is f prime of g of x. Okay, so let's start by finding the inverse. Your original function can be written as y equals x to the fourth plus 10. Find the inverse by swapping x and y, and then solve for y. negative, but just to the 1/4. Okay, so you got g, and now you need f prime of x as well before we plug anything in. F prime of x equals 4x cubed. Okay, so now we can go to our formula, which will be g prime of x is 1 over f prime of g of x. So 1 over f prime is 4x cubed, so 4 g of x cubed. And that means 1 over 4. Remember that this thing here is g of x. It's 1 over 4 x minus 10 to the 1/4. If you wanted, you could rewrite that as a negative exponent. 1 over 4 x minus 10 to the negative. Oh, excuse me, sorry, that should have been 3/4. Because it's g of x raised to the 3rd. Okay, so now it's all of this to the negative 3/4. Note that that actually would have been what you would have gotten using the power rule here, if that was your g of x. So this case, you technically didn't need the formula, but I just wanted to show you how you could use it. Sometimes you really do need it. So let's look at when that happens. Okay, so here let's find g prime of 1, where g is the inverse, and f of x is x plus e to the x. Okay, so let's just write it out. So g prime of 1 is 1 over f prime of g of 1. That's the formula that we found. Okay, well, I can get f prime pretty easily. That's just 1 plus e to the x. G of 1. How do we get g of 1? Well, remember, g of 1, it's the inverse of 1. And so g of 1 is some number. Well, we know that f of some number then is 1, because g is the inverse. So what do you plug into f if f is x plus e to the x? What do you plug into that to get 1? Why don't you try 0? F of 0 is 0 plus e to the 0. Well, e to the 0 is 1. So actually, 0 is your answer here. So g of 1 equals 0. That means that g prime of 1 back here is 1 over f prime of 0. Well, we know f prime over here on the right is just 1 plus e to the x. So f prime of 0, 1 plus e to the 0, or just 2. So after all that, we can then confidently say g prime of 1 is 1 over 2. Never even had to figure out what g of x was equal to, but we could still figure out g prime of 1. Okay, a really neat application of this understanding is figuring out what are the derivatives of the inverse trig functions. So let's write that out. Derivatives of inverse trig functions. Okay, so I'll give it to you and then we'll prove it. The derivative of inverse sine x. Actually, why don't we prove it first? So I'll leave it blank. Derivative of cosine inverse x. Something else. Okay, so we'll fill that in just a second. Okay, well, let's I could just use my formula, but I want to show you just the principles of like how we got our original inverse derivative formula, how that can be used in case you forget it. So we're looking for the derivative of inverse sine. We can start with this simple principle. Sine of inverse sine of x equals just x. They cancel each other out, so to speak. Take the derivative of both sides. So on the left you get cosine of inverse sine x times the derivative of inverse sine x. And the derivative of the right side is just 1. So then you just solve for the derivative of the inverse sine of x by dividing. So derivative of inverse sine x is 1 over cosine inverse sine x. Let's not leave it like that. So remember, the inverse sine function is asking what angle did you take the sine of to get x? So it gives you an angle. So let's say let theta be that angle. What angle did you take the inverse sine of to get x? Well, remember that sine SOHCAHTOA is opposite over hypotenuse. So you can actually draw a triangle, label theta here, and say, well, inverse sine of x, opposite over hypotenuse, would be x over 1. Use Pythagorean theorem, a squared plus x squared equals 1 squared, to solve for that missing side, which we'll call a. So a squared equals 1 minus x squared. And so we'll take a to be equal to the root 1 minus x squared. As you can see, the way we've drawn this triangle, it is positive. Okay, so then we said, okay, up here, derivative of inverse sine x is 1 over cosine inverse sine x. So what's the cosine of that angle? Cosine of that angle is just root 1 minus x squared over 1. Okay, so then the derivative is 1 over root 1 minus x squared. So we'll fill that in. Pretty neat. I forgot to write my QED. Okay. So let's actually do this exercise. I'm going to show you that inverse cosine is just the negative of the derivative of inverse sine. So let's look at a proof. So let theta equal inverse sine x, and we'll use the Greek letter psi equals inverse cosine x, but you haven't seen that Greek letter before. So we'll draw a triangle, just like the first one. Okay, theta. So sine is opposite over hypotenuse. Now just looking at the triangle, we can see, wait a second, there is an angle where you have the adjacent over the hypotenuse that's x over 1. And that would be our cosine, x over 1. So we can actually just label psi in the same triangle. Well, since all the angles add up to 180, and you already have a 90-degree angle in there, therefore, we know that theta plus psi equals pi over 2. And that means, based on our definitions, that inverse sine x plus inverse cosine x is always equal to pi over 2. So this is where it gets kind of cool. Since we want to find the derivative of inverse cosine, we solve for inverse cosine. And take the derivative of both sides. So the derivative of inverse cosine x is the derivative of pi over 2 minus the derivative of inverse sine x. Well, the derivative of pi over 2 is just 0 since pi over 2 is a constant. And we already found the derivative of inverse sine x, so we know then it's just negative 1 over root 1 minus x squared. So that is pretty neat. Alright, a couple more problems. So, let's see. Another example. Find f prime of a half if fx equals arc sine x squared. So if you haven't seen it before, arc sine is just a different way of writing inverse sine. Okay, so when we find our derivative, we're going to have to use the chain rule. Derivative of arc sine is just 1 over root 1 minus x squared. But instead of x, the input to arc sine is x squared. So it's got to be x squared squared. All of that times the derivative of the inside. This is the chain rule, by the way. So 2x. So your final answer would be, well, not final, but the derivative would be 2x over root 1 minus x to the fourth. Okay, so then we can conclude that f prime of a half, 2 times a half, over root 1 minus 1 half to the fourth, gives you 1 over 1 minus 1/16. It's 15/16, which will just be 4 over root 15, because I'm taking the reciprocal of root 15 over 16. Okay. I'm going to give you some more inverse trig derivatives, which you can prove at other times. So this is just more trig derivatives. So the tangent just gives you 1 over x squared plus 1. Cotangent works out to be just the negative of that. Derivative of inverse secant. A little weird. It's 1 over absolute value x times root x squared minus 1. And then the cosecant, it'll be just the opposite of that. Just the negative of that. So then you could do a problem like this. So I'll put that in the bubble for you. Those are some good derivatives to know. The derivative of cosecant inverse of e to the x plus 1 evaluated at x equals 0. So, just try and keep your head straight. You've got to do some chain rule, and it's going to look a little strange. So just pretend like e to the x plus 1 is just an x. So following your cosecant inverse derivative formula I just gave you, it would be negative 1 over absolute value of x, but in this case it's e to the x plus 1, times the square root of x squared, so that'll be e to the x plus 1 squared minus 1. Now times all of that times the derivative of the inside, which just turns out to be e to the x. Don't forget we're evaluating at x equals 0. So for the next step, you can just plug in 0. So negative e to the 0 over absolute value e to the 0 plus 1 times the square root of e to the 0 plus 1 squared minus 1. E to the 0 is just 1, so you get negative 1 over absolute value 1 plus 1 times the square root of 2 squared, 4 minus 1. Comes out to minus 1 over 2 root 3. Great. And your homework that will go along with this will be page 181. Numbers 3 to 13 odd, 19, 21, 25, 27. And that is all. I will see you in class Monday and Tuesday.